Yeah, we only have 4 people, so feel free to ask question at any time. And yeah, we can have more discussions. Okay, so today's discussion is about RISC-V pipeline, and there's also another one tomorrow, held by Harrison. So the main point we want to use pipeline is we want to improve the performance. So like I mentioned in the first discussion, so in digital design, if we just increase the clock speed, if we just increase the clock periods, we don't have to like change any other stuff, and the performance will just doubles. But we cannot like just rely on the advance of technology. So we have to like if we only like try to make transistors smaller and smaller and then increase the clock speed, then there's actually the space is very limited. So we have to have some like architectural innovation. Pipeline is just one of them. So if we take a look at the diagram here, for a single cycle CPU, so all of the 5 stages have to like fit in one clock cycle. Your clock will be something like this. That means you're basically have a like 1 nanosecond clock, and that will give you 1 gigahertz CPU. But as you can see, so during this time, the hardware for fetch instruction is basically idle. So the idea is we want to keep all of the components busy, and that's why we introduce pipeline. So as you can see here, at each cycle, basically every hardware is executing one of the instruction. So by using pipeline, our clock is basically something like this. So now we can clock much faster, and like the time scale here, this is something like 1 nanosecond. But for this one, this is like 0.25 nanoseconds, which means we have around 4 gigahertz CPU. So yeah, that's the very basic idea of why we want to use pipeline. And so for sure, it will bring more challenges. Like your design complexity is much harder than this one. And you also have to like there are new issues bring up by using pipeline like hazard, which we will cover later. And your clock is actually determined by the longest stage. So now we have a 5-stage pipeline here. So what if we want to use like more stages? We have to like do pipeline inside of these stages. Like we can do pipeline inside of a memory, or even we do pipeline inside of an ALU. So modern CPUs can have up to like 20 stages. So that's true even for 10 years ago. So for a CPU like i7 made by Intel, like have 20 or 25 stage pipeline. All right, any questions about this one? All right, cool. So this is a review of what the complete data path looks like. So for a 5-stage pipeline, or so during the previous class, we explicitly like divided all the data paths into 5 stages. The first one is instruction fetch, which is IF. We want to get the correct or the current instruction from the instruction memory. And the second one is decode. Decode is basically gets every values ready, like read all the values from the register file or gets all of the immediates ready. And next is execute. So this stage stops here, right after when ALU gives a correct answer. And next one is memory access. MA or just M. So memory access, basically, we need to like fetch the desired data from the memory. And it actually stops here, right after the mux gate. And the last one is write back. So yeah, so for a 5-stage pipeline, so what we do is basically we just add registers between these or among these stages, which is shown in the next page. So what I want to mention in this in this slide is so we ignored all of the control logics, like the control logics for ALU, for the muxes, for the register files, for the memories, for the write back select, and the branch compare. So these signals are also required pipeline. So let's say we have a control logic below. So how are we going to implement these signals? Any ideas?
We have instruction
Mhm.
at that time step. So, but
Should be here, right?
yeah.
Let's say we have some combinational logic
Yes,
inside of this one. And
yeah.
this combinational logic can give all the outputs for these control signals, right?
Okay, then we can keep those output in register.
Yeah, right. So let's say for the write back, oops. So let's say branch comparison. This one is much simpler. So we also have to like register this one.
Yeah,
right?
yeah. Yes.
And also register this one. And for the write back, it actually requires more delays because write back actually happens at the very last stage. So we want to make sure that all the timings are correct. So the basic idea is, yeah. So the basic idea is just make all the control signals arrive when they're needed. That's how we can like make sure the data path, the pipeline data path works correctly. Okay, so the next topic is hazards. We mentioned 3 types of hazards in the lecture. So the first one is structural hazard. Structural hazard is basically a single resource is required by more than one instructions. We have kind of solved this kind of structural hazard issue. Like we have from the very beginning, we're using register file with 2 reading ports. So when we do some R type instructions like add, RD, RS1, and RS2. So basically 2 source registers are required. So we have 2 reading ports. That's how we avoid the structural hazard in R-type instructions. And the second one is data hazard. This is the most commonly seen hazard in a pipeline data path. So basically, data hazard is one or more source register is not ready when it's being used. When it is being used. So this is basically write after read problem. Let's say we have something like this, add x3, x1, x2, and we use the destination register right after. Like we are doing something like this, x1 and x3, and x3 is not ready. That's when a data hazard is happen. So data hazard can be solved by using forwarding, which is add more hardwares or add more data paths. That is treat complexity for performance instead of just wait and stall the whole pipeline. And the third type is control hazard. So for the branch instructions, like say be equal or be less than. So once we start executing a branch type instruction, we cannot know if it is taken at next cycle. So we have to like wait for the comparison module like this. We have to wait for the result of this guy. So we can only know the result at the end of execute. At the end of execute stage. So during the waiting time, we can also do some stuff like we can assume the branch is not taken, which means if we have some instructions like this, so we have a branch instruction, and then we follow by some other instruction. Yes, I think it's 2. So when branch is taken, let's say we have a 5-stage pipeline. Instruction fetch, decode, execute, memory access, and write back. So when this one is executed, we can just perform or execute the following ones. So at the end of this stage, so when the compare module, like when it gets the result, whether we are taking that branch or not, we can just so if the branch is taken, we will just load the correct instruction and kill all of the rest. So this will be killed. There's also more. There are definitely more things you can do for instead of just assume all of the branches are not taken like this. You can do something like branch prediction. So for commercial CPUs or CPUs on market, there are much more complicated strategies for branch prediction. And that's how they make difference or compete with each other, with other companies. We will have some examples in the following slides. So let's start with data hazard stall. Assume we are using stall to solve the data hazard. We're just doing nothing and wait. Anyone want to try this? I can mark the, or we can like, so where the data hazard happens on the left assembly code.
XOR is X3, which is output of first addition.
Okay, cool. That's one of them. And
the other one is OR and XOR, right?
Yeah, right. Correct. So yeah, let's just fill in the table and see what happens. So for the first cycle, we just the add instruction is in the instruction fetch stage. Then we just proceed with subtraction, add, and then we can keep going, XOR, sub, add, which seems fine. And next cycle, so we are doing OR, XOR, sub, add. So can we proceed next cycle? Like, can we push the OR or XOR to the next stage?
No, the result of addition is not still.
Yeah, right.
Yeah,
so the result of this add is only available when add is pushed to the write back, right? So the XOR, so one of the register used by XOR is not ready yet, so we have to like stall. So the rest can keep going. So at the end of this cycle, the X3 is actually ready, right? So we can keep going like This is OR. This is XOR. Still do nothing. And this is sub. Yeah. And for the next cycle, the OR actually using X5. X5 is the result of XOR. So again, we cannot proceed for the OR instruction. We have to apply stalls. So OR can keep going when XOR reaches the write back stage. And it will keep going until finish. So it actually takes 11 cycles to execute this 4 assembly code, which means our CPI is 11 cycles divided by 4 instructions, which is 2.775. Any questions? Okay, cool. So like we mentioned before, all data hazard can be solved by using forwarding. So let's just consider the most simple case like this. If we have 2 instructions, in which X3 is used just in the next cycle. And we can draw the timing diagram here. So for the add instruction, number of cycle. So in cycle 1, it is doing instruction fetch. In the second, it's doing decode. So if we don't have any hardware for forwarding, we can only do execute after the write back when this is finished. But we know that actually X3 is already calculated at the end of this cycle, right? So we can do forwarding from here to here. And so if we can somehow add add a data path, like forwarding the data executed by at this stage and forwarding to the next instruction, so we can somehow result like this. So there will be no punishment for data hazard, right?
So quick question. For the graph you have without data forwarding, cycle 5 is write back, cycle 6 is execute. Shouldn't it be like cycle 6 should be instruction decode? Because that's when you're reading the register files, right? So you write back in that cycle, and then the next cycle you actually find out what the content is.
Yeah, that can be true. So for the register file, we use in the class. So the read port is asynchronous, but the write port is synchronous, right? So if you write into it and then read from it, so whether you can get the correct result, it actually depends on the spec. So if you actually doing a homework or an exam, you need to like pay attention to the instructions. Like it will be specified whether it is supported or not. So
Okay,
here we just So here we just assume we can. So when we are writing it, we can do a decode here. So that means at the end of this cycle, the correct value can be decoded from here. So we can perform executing right after. Does that make sense? Okay, cool. So the hardware for this is quite straightforward. Let's say we have a ALU, something like this. So we know one input can probably come from PC or from RS1. And the other input is either from RS2 or an immediate. And at the output is just a register, which is the end of executed stage. So if we want to do data forwarding, like if we want to make sure that the data or the results we get from here, it will be feed directly into the next stage, the stage of execute. What we can do is something like this. We can just use a 3 input mux and forward the data from here. And also we have to like use some logic. So we have to like see whether it is the same register being written from the last instruction and then used in this one. So it can give the correct control signal. So that's the most simple hardware we can do. Any questions regarding this? Okay, cool. We may also want to do something like this. So it's possible that another register is using the forwarded value. So yeah, we have to like consider both of the inputs. Okay, cool. So we can move to control hazard, the next topic. So for this data path, this is given by Sophia's lecture slides. So for this data path, how many actual cycles are taken if a wrong prediction is made? Anyone want to try this one? Let's say we have some instructions like equal x1, x2, immediate, and then we have some other instructions like instruction 1, instruction 2, instruction 3. And x1 and x2 is actually equal at the very beginning. Let's say it will jump to here. Something like this. Yeah. So if we assume that PC plus 4 is always taken, which is equivalent to branch not taken. So how many extra cycles are there?
Two.
Okay, why this 2?
Because when this branch is evaluated, some instructions are in decode and fetch. So these two instructions should be cleared. So we use two instructions, two cycles.
Okay, cool.
Right.
Let's see. So it might not be very like straightforward by just making observations. So let's say this is still a 5-stage pipeline. We have instruction fetch, decode, execute, memory access, and then write back. So we are doing BEQ at the first cycle. And then for the second cycle, we actually, because we are assuming branch is not taken, we'll just proceed. For the third one, this is instruction 2, instruction 1, be equal. So at the end of execute, so at the end of this cycle, we're actually knowing that this branch should be taken because we know x1 is x2, right? So, but the result is actually pipeline and feedback here. So it actually is in front of the PC. So after this cycle, we cannot actually get the correct instruction because we also have a register at the very beginning. So this actually this is gonna waste one more cycle for it. But yeah, because at this cycle, the data actually travels from here to here. And then at the next cycle, we can get the correct instruction. So actually there will be 3 extra cycle. That's only true for this data path. That is because we are actually implemented the PC in this way. If we are like forwarding the ALU, not from the output of the register, but from the input. Let me make it more clear. So we are actually feeding back the ALU from here, but actually if we feed back the value from here, that will only result in like 2 extra cycle. So this will be 3 and this will be 2. Does this make sense?
Yes.
Yeah, and this is a tricky question. Yeah. Just the point is just make sure you have like understand the data path. So, but so when you're like designing a CPU like in your project, you don't have to do it this way because it might be a little confusing. Just make sure your timing is correct and you'll be fine. So it can either be 3 or 2 depending on the setup of the data path. Okay, cool. So we have another practice. Anyone want to try this one? Any volunteer? Just assume we are using the same hardware than this one. So there will be 3 extra cycles. Okay, I'll do this. So at the beginning, we are doing be equal. X1 is actually equals to X2 according to the problem setup. This will be add equal, then sub add equal. The branch actually actually we know the results of the branch at this cycle, but because we're using this hardware, oops, my screen froze. Can you hear me? Oops, sorry, my network has some issue. Can you see my screen now? Sorry about that.
Yes.
Okay, cool. Okay, as we mentioned before, so each run prediction will take three extra cycles. So we're actually, the new instruction will be available like after. So we know the results here, but we have to like wait for one more cycle before we can get the instructions, get the correct instructions. So be something like this, and at the next cycle, this will be killed, and we load the correct one. And then just proceed.
So can you argue that for branch equal, it doesn't really need to have a write back stage. So at that point, you can just flush it anyway.
You mean at stage 4 or at cycle 4?
Sure. Cycle 4, cycle 5.
So it doesn't use memory access and write back, so we don't actually need this.
Right. So what I'm saying is, instead of just flushing XOR and sub, you can also flush bench equal, because as long as you have the new C, you're good.
Yeah, sure. Yeah, you can definitely do that, because these branches are not doing anything in these two stages. Yeah, you can do that.
Right. And in that case, like the implementation is just going to be easier because you just flush pretty much everything down the pipeline, right?
Correct.
Okay.
Yeah, that's a good point. Okay, that is the branch not taken. And we also have an example for a branch taken. It is exactly the same problem setup than the previous one. I'm gonna pass this one. So if branch is taken for default, basically this line will be equal. And then because we have some forwarding hardware, we can directly jump to the branch. So this line will be all added, and it will finish just like this. All right, cool. So as we mentioned before, we have some forwarding hardware, so we can make sure that the branch address is available right at the next cycle. Any ideas how we are going to implement this hardware, like where it has to be? if we want to make sure that the address is directly available from here. Any idea?
That instruction fetch.
Exactly, yeah. We have to like add extra hardware here. Some like calculation for address by using the instruction directly get from here and then feed it back to here. So this will probably make a very long critical path because we know reading from memory is kind of slow, but this will work. Any questions? Okay, cool. So we also mentioned that we can make some branch prediction, like instead of just assuming branch is taken or not taken. So we can, so a very simple but useful strategy is we can based on the last choice. So why it is useful, we can consider this code. So this is just a for loop. It's adding one from 1 to 100. This is the equivalent C code. And so we can see that at the end of, so every time it's just a count. It just compare the x2 and x10. And if it is not equal or if it is still less than, it will jump back to this line. So as we can see, this branch is actually taken for the first 99 times. It is only not taken for the last one, right? So if we are making decisions using the previous choice, it is quite efficient because we know in some loops or in some useful cases that so some comparison results will be the same. So yeah, this basically shows the idea. And we have one more question. So I'll give you some time to read. This is a register file. So the reads and writes are both synchronous. What is the possible issue with this implementation? We don't have to like consider the data hazard. This is even not correct. So all parts are synchronized. Are synchronous. Okay, go ahead.
Data come after one cycle after the address is inputted, right?
You mean this cycle comes after?
I mean D1, D2 is outputted one cycle after.
Yeah, right.
R1, L2 is inputted.
Okay.
So this may go through.
Yeah. So yeah. So at the if we draw out the clock, it might help us understand. So at this edge, D1, D2 are available, right? And at this edge, the output from ALU is available. Let's just call this ALU. So at this cycle, we should write back the desired value because this is ALU. Actually, we should write back at this cycle, right? But we don't have any registers here. So this is not correct. We have to like add 2 registers to make sure that this write enable and write address is aligned with the data we get from the ALU. Does it make sense?
Can you repeat it?
Yeah, sure. So let's say all of the input signals are coming together. D1 and D2 are delayed by 1 clock cycle, right? Because we know it is synchronous. So D1, D2 will be available after it sees a rising clock edge, right? And the signal here, we call it ALU. It will come 1 clock after D1, D2 is available because we have a register here. So when this data is ready, it actually passed 2 clock cycles. So this is the data write. So we also have a signal that control if we should write into our register, which is called write enable. And we also have a write address. So these 3 signals, they should be aligned with each other. So they should arrive on the same time. Because our ALU is delayed by 2 clock cycle, we should do the same for the write enable and write address. So we need to add 2 more registers for these 2 signals to make sure the data path actually works.
So one for ALU and one for clock, right? One for the register after ALU.
This is already there. This one.
Yeah. I mean the cycles. One cycles come from ALU and the other.
Yeah, correct. Exactly. Yeah. The register file. Yeah, that's because we have synchronous reads. That's the setup of this question. Okay, cool.
So if we read is not synchronous, we only need 1.
Exactly. Yeah.
Okay. Yeah, I understand.
So for this part, we have asynchronous reads, just like your question, and writes are still synchronous. And we want to add appropriate forwarding hardware to eliminate all the data hazards. So now we only have 1 register, right? So this is actually, it can, so the data path actually works, but we want to like try to solve the data hazard. Any?
Can we just get rid of? Can we just get rid of register after ALU?
Get rid of this one.
Yeah.
No, because this stage is actually execute, right? We still have to make sure the output is registered. So if we get rid of this guy, we also have to get rid of this guy to make sure the logic, to make sure that they are aligned in time. So actually, the data path is something like this. You have some input address, and then it goes through ALU and then feedback, and comes back here. And it should have the same, time just as the single wire. And that is not very reliable. And that's why we add registers for both.
Shouldn't ALU also take 1 clock cycle?
No, ALU is just some combinational logic. It's just some gates. It will, yeah.
Because previous one, we assume AL take 1. Oh, it's.
Wait, this one?
Yeah.
Oh,
so
that is.
So first one, we assume ALU takes 1 cycle, and then the rest is also.
No. So the first delay is by register file, and the second delay is by the register after ALU. because we have synchronous reads. Yeah.
Okay. So for the next one right here, if we do the same thing, right, we have RF in here, and then we have another register. Don't we already have two here already?
We have, so in this one, we have asynchronous reads.
Okay.
So there will be no delay from the register file. There will only delay from ALU. The register after ALU, I should say. Yeah.
Okay.
Okay. So this is pretty same as the previous one. So I'll just draw out the diagram because so if we want to implement the forwarding, we have to like forward the output of ALU to its input, right? That means we need to add some gates. So let's say this is 0 and this is 0. And if it is 1, we want to take the updated level. The updated one from ALU. And we only need to like design the select. Let's say this is A, this is B. And I'm gonna call this guy select A. And this guy is select B. So we have to like compare if the input of A is the same as the previous results. So we are going to use a comparator here. And if it is the same, and we also want to make sure we write into the register in the previous instruction. So we want to end it with the write enable. And that will be our select A. And for select B, it's just the same thing. We just do it for signal B. And this one should come from here and here. Okay. I think that's all for today's discussion. Thank you for attending after your midterm. I will hold my office hour right after. If you have more questions or you have some questions regarding homework or something else, you are free to stay. And that's all for today. Thank you.
Thank you.